Now, deformation can take place in many different ways. You can have a compression or a tension pulling an object apart or squeezing it together. You can have a shear force where you place a force perpendicularly on the object, like my example with the diving board I used in the last video. Or you can have a bulk modulus where you have pressure on an object squeezing it down in all directions and not just in one direction. So we'll look at all three of those types of deformation. The first we're going to look at is tension and compression, changes in length. So imagine you have some kind of a steel rod or the cross-section of a cable, and the cable has some cross-sectional area A, so that's the thickness of the cable, if you will. If you cut it, what's the thickness of that cable? And we're just using a simple circle here to make it simple. And you have some initial length L0 of the object before the forces are applied. So imagine this is like a steel column or even a concrete column. If you place a force of compression, so a force upward here and downward there, equal and opposite. In other words, if you squeeze the column, deformation occurs. The column will get a little shorter. It'll change by some amount, delta L, from its original length of L0. So imagine this would be like a steel column in a building. Toward the bottom of the building, holding the weight of the building up, you can have some compression in that column, or a bridge support. So materials, how much they compress depends on the type of material, and we'll talk about that in a moment. Alternatively, you can stretch an object, right, through tension. So imagine a steel cable coming down with a wrecking ball at the end of it. Well, before that wrecking ball was attached, it was just a steel cable of some length. But when you add a wrecking ball at the end, that causes force of tension in both directions, right? The wrecking ball is pulling down and the crane is holding up that wrecking ball. That puts a tension in that cable, stretching it out slightly. So the cable will get longer by some amount delta L, again depending on the material that we are looking at. So how do we figure out what delta L is? Well, we could simply look at it this way, right? The change in length, the equation given here, the change in length is equal to the original length. So we need to know how long the object originally is if we want to know how big the change is. So an object 2 meters long will have twice the deformation of an object 1 meter long. We need to know the force that's applied. That makes sense, right? No force, no deformation. So the greater the force, the greater the deformation. It's inversely proportional to the cross-sectional area. And the way to think about that is, imagine this is a cable. The thicker the cable, the less likely it is to stretch, or the less stretch that you get out of a thick cable. So very, very thin cables will stretch quite a bit. Very thick cables, not so much. And then finally, it's inversely proportional to this variable y. This y is called Young's modulus. Young's modulus is material dependent. And sometimes, even based on the material, it depends on how you treat the material. For example, stone is really good in compression, awful in tension. These are values you need to look up, or you'll solve for the unknown Young's modulus. So steel has a larger Young's modulus than, for example, lead. Lead is very malleable. Gold is very malleable. So depending on what you're making your bridge out of or you're building out of, you'll have a slightly different Young's modulus. And when you're doing engineering, most of you are health sciences, of course, but engineers need to worry about the lengths of those objects. Like, for example, bone, right? Bone has a Young's modulus. Bone is compressed or stretched. Extreme example of this, and it's not just bone, astronauts actually come back taller than when they leave. That's largely also due to the cartilage between the bones relaxing and expanding. But bones, your leg bones are under compression right now. They are shrinked a little bit from what they would be if they weren't in that state. So this is changes in length from tension and compression using Young's modulus. We're going to continue and look at what happens when you have a shear force applied in just a moment. So moving on to sideways stresses. the shear modulus. Again, using my diving board example, because that's an example most of you probably have some familiarity with. If you have a diving board that should be, under its own weight, rigid and horizontal, as you walk out to the end of the diving board, you place a force downward on the end of the diving board, deforming it, right? It bends down, shown here in blue. And again, not an artist, so bear with me. How much it bends is delta x, although it is in the y direction, you could say it's delta y, but we're just looking at one-dimensional motion. Your book calls it delta x, so we'll stick with it. This delta x motion, how much does it deform? Well, you could imagine it depends on the weight of the person, right? The force downward depends on the person's weight. Someone who weighs more will deform the board than someone who weighs less. You know, a 6-year-old running out to the end of the board won't cause it to bend as much as an adult. It depends on the cross-sectional area once again. The shape of the board itself. Most diving boards are standardized, but if you have a thicker diving board, it would not bend as much. A thinner board would bend more. It depends on the length of the board. A deviation here of 1 centimeter if the board is 2 meters long. If the board is 4 meters long or twice as big, that deformation should be twice as big. So the equation for shear modulus is given here on the right. The amount of sideways motion compared to the length of the board depends on the length of the board, depends on the force applied, and is inversely proportional to the area, just like it was with Young's modulus. The only difference is we're not using Young's modulus here. We're using S, which is called the shear modulus. And again, this is dependent upon what the material is. Young's modulus and shear modulus are different for different materials, and they're different for the same material. A material with a Young's modulus will have a different shear modulus. Some materials are wonderful in compression, but suck with shearing forces. Brick is one of them, concrete, marble, rock. If you ever wondered why, if you've ever been to ancient Greece or seen Greek Colosseums, they have a lot of columns of marble very closely spaced together because the supporting marble, the cross sections of marble, or rock or granite or whatever they're using, you can't span a very big area before the shear forces cause it to snap. Now we have modern engineering techniques that can dramatically improve our building techniques, but back in ancient Roman times, they did not have that. They just knew that marble and rock was wonderful in compression, sucked for shearing forces. Now, one thing I didn't mention earlier in the video, but I want to hit one up again, the ratio F to A. And you'll see this ratio, force over area, in the 3 different types of stresses and strains we're talking about today: Young's modulus, shear modulus, and in a moment, bulk modulus. All have this ratio F over A. That's called the stress. The stress that's being placed on an object. The stress is proportional to the force, so more force, more stress on the object. That kind of makes sense. And inversely proportional to the area. Thicker objects, or objects with a thicker cross-section, can withstand more forces. Right? Trying to snap a large, thick branch is different than trying to snap a pencil because of the shear forces. Thinner pencils, for the same force, gives a larger stress. The ratios of the change in lengths with respect to the original length from compression and tension, or the change in sideways position with respect to the original length, in the case of the shear forces, these are called strains. This is the strain that the object is under. So stresses cause strains. So it's a relationship between stress and strain in physics. Now there's one more we're going to talk about dealing with bulk modulus, or what happens if you're to an object under pressure. Finally, we look at what's called the bulk modulus. Now, the bulk modulus relates the volume of an object with the pressure placed on that object. So as the pressure changes, the volume of the object will change. So here we have a cylinder of some volume V naught. When placed in a fluid at high pressure, imagine this thing descending into the oceans, forces act in all directions on this object, squeezing it down, causing its volume to change. Now this little dotted line might be a future volume. The cylinder gets smaller in all dimensions. So there's a volume change. So the change in volume experienced by an object depends on the object's original volume, force over area, the stress once again on the object. But in this case, the stress is not a lateral stress for the shear force or compression or tension. F over A here is the pressure that this thing is under of the fluid. So pressure pushes in all directions, and we'll talk more about pressure when we talk about fluids later on this semester. However, fluids, to give you an idea, right now you're sitting at the bottom of a sea of air, right? The Earth's atmosphere extends way above your head, and you are experiencing 14 pounds per square inch of pressure. So every square inch on your body, there's 14 pounds of force pushing on it in all directions. That is atmospheric pressure. The higher the pressure, higher F over A, the greater the change in volume. And then finally, this also depends on a constant once again. Like with compression and tension, we had Young's modulus. With the lateral shear force, we had the shear modulus. Now we have what's called the bulk modulus, B. And again, this is something you need to look up in a table. Depending on the material, you can have quite a variety of different bulk moduli. Some material is easily compressible, others is not. One dramatic example of this might be if you've ever seen the Red Bull jump, Felix Baumgartner's jump. He got into a weather balloon, went to the top of the Earth's atmosphere, basically, and jumped. Well, here, at high pressure, at the bottom of the atmosphere, the weather balloon was actually very thin and very small and didn't take up much volume. At the top of Earth's atmosphere, the weather balloon expanded to take up a great deal of volume. So the change in volume was actually negative as the pressure decreased. Or playing it in reverse, a weather balloon at the top of the atmosphere has a huge volume. Bring that same weather balloon down to the bottom of Earth's atmosphere, the pressure squeezes it down into a much smaller volume. Another example, if you know anyone in the military, particularly the Navy, submarines will will occasionally have a line from one end of the submarine to the other end of the submarine, a cable that's taut when the submarine is on the surface. But as the submarine descends into the icy abyss and the water pressure increases and gets greater and greater and greater, the entire submarine, the canister you're in, gets smaller. Its volume changes. It gets smaller, and now this cable that was taut is now hanging quite loose. A really wonderful, dramatic example of the volume change due to high pressure in a fluid.